Let's go ahead and take a look at our electrons. Now, looking at our electrons, this is going to get a little bit more complicated because electrons are very weird because they have characteristics of particles and waves, and this makes them pretty unique in the universe. And due to their strange nature, whenever we talk about electrons and their locations in the atom, the Bohr model, which is the most common model that we see, is not really sufficient in order to describe where those electrons are. And what we need is going to be the quantum model. Now, the quantum model of the atom provides us regions or rooms where electrons are most likely to be found. And so this goes back into the idea of kind of Heisenberg and his uncertainty principle, Schrodinger as well, of where we don't know exactly where the electrons are and what speed they're going to be at. Okay, we only have a probability of where they are going to be located. And those and everything are going to be these rooms or these orbitals where the electrons are most likely to be found. And these orbitals do have certain shapes to them where they can be found. And they do get a little bit weird. So, taking a look at our S, P, and D. So, our S orbital is going to be just a sphere. Our p orbital will look like a dumbbell, and then the d orbital is going to be this flower shape to it. Now, let's look at everything at a three-dimensional model of this just to help kind of visualize what these look like. Because whenever we need to visualize these, we can't just think about two-dimensional, we have to think three-dimensional with it. Let's take a look at some of the three-dimensional aspects of the electrons in the quantum model. So starting off with like the basic is going to be hydrogen. So our hydrogen just is looking like a sphere. Now, as we add in like helium, we're adding in a proton, adding in another electron, the cloud is going to grow just a little bit. Getting into lithium, we're adding an energy level, so we're adding in more space into the atom. Same thing with beryllium. Now, this right here in this grayish beige color is going to be the s block or the s orbital. And so the s orbital is going to look like a sphere. Now, getting into the p orbital or the p block, this will be this pinkish color. So if we take a look at boron, now we have introduced this dumbbell shape from it. Now, as we add more electrons, we can actually add in more orientations. So we have this one orientation right here. If we add in another electron, we now get more of these dumbbell shapes. So this is being able to hold two electrons within the p orbital here. Now, if I add in another electron, we end up with this three-dimensional flower type of shape. And this is able to hold three electrons within these red dumbbell shapes. Now, each of these is able to hold a maximum of two electrons. And so as we go to like oxygen, fluorine, and neon, the shape itself doesn't change, but we are adding in more electrons into these orbitals or these rooms. If I move down to sodium, we're adding in another sphere to layer on top. Magnesium, the exact same thing. And then for the P block, we still get those larger dumbbell shapes, being able to add in more space. And so all these orbitals are just essentially being overlaid on each other, getting larger and larger as we are increasing the size of our atom. Now, if we take a look at potassium, it grows even larger, calcium, a little bit larger as well. Now, this right here in the blue is going to be the D block. And the D block does get a little bit crazy. So, looking at this one, we have our dumbbell shapes, but this time we're adding in essentially four immediately. Going to like titanium, adding in another layer, we get this flower-ish type of shape to it. Add even more to it, and we get this really large shape being able to hold a lot of different electrons. Keep on adding more and more. We just overlay these orbitals a little bit more, and it just gets a little bit larger from it. And then if we keep on going, we can keep on adding more and more, and we get this really large overlay of these orbital rooms. And that is going to be why, whenever looking at the quantum model, we have to think a little bit more three dimensionally, because this is going to look pretty different than the normal Bohr model. So, if I take a look at titanium, so we get less of those orbitals in it. But if I take a look at the Bohr model of this, it essentially looks like this, with the number of electrons on the outside. And so the Bohr model does have a lot of benefits to it, because we are able to count the number of electrons, we are able to count the number of energy levels that titanium has. And so the Bohr model is super useful for its simplicity, especially when comparing to the actual quantum model, which gets very confusing very fast just because of how many different overlays it has. Now that we've taken a look at the diagram, the simulation of those orbitals, let's go ahead and take a look at their number of orientations and the maximum number of electrons that they're able to hold. So in our s orbital, we end up with one orientation just because it's a sphere. And the s orbital is able to hold a maximum number of 2 electrons. The p orbital has 3 orientations to it. Each orientation is able to hold 2 electrons, so we get a maximum of 6 electrons. The d orbital has 5 orientations to it. Each of those orientations again holds 2 electrons, making the maximum number of electrons to be 10. And then we have the f orbital, in which case we have 7 orientations. Each of those orientations can still hold 2 electrons, which means we have a maximum of 14. Now, what we're going to get into is going to be the electron configuration of this. And the electron configuration describes where all of the electrons are located in the electron cloud. And so what we're going to end up having is going to be this 1s2, 2s2, 2p1, and that configuration is going to show that this atom is boron. Or if we take a look at boron, it has this electron configuration, meaning that in the first orbital, in the s orbital, we have 2 electrons. In the second s orbital, we have 2 electrons. And then in the second p orbital, we have 1 electron. Now, breaking this down a little bit more, we have the large number out front, which is going to be the energy level that we are in. The letter will be the orbital. So we have our s, p, d, and f orbital. And then the superscript is going to be the number of electrons in that orbital that we have. Now, there are a few rules that we do have to abide by whenever looking at the electron configuration. And the first one is going to be Aufbau's principle. And this states that we need to fill the orbitals from the lowest energy level to the highest energy level. And this does make sense. Think about building an atom from the ground state. We're going to start from the lowest and then we're going to build it up. And that is essentially what Aufbau's principle is telling us to do. Next is that we do have Hund's rule, which states that we need to maximize the unpaired electrons. We want to fill all the orbitals of a sublevel with 1 electron first and then add a second. And so, for example, if we have the D sublevel, we want to have all of the electrons in the up position, taking up each space and not just kind of randomly throughout. The best way to describe this would be if you're getting on a bus and you don't like anybody on that bus, you're typically going to sit one person per seat until the bus is full and you have to pair up. So electrons don't want to pair up unless they have to. And that goes back to the idea of their charges. So we have our electrons being negatively charged, so they are going to want to be as far apart as possible. And then we have the Pauli's exclusion principle, which states that no two electrons have the same quantum number, and so they have an opposite spin within the same orbital. So we have an up spin and we have a down spin. And this is just designed to make sure that the electrons are maximizing their space away from each other. Let's go ahead and take a look at the electron configuration. But first, before getting into it, let's make sure that we know where the different blocks are. So the first is going to be the S block, which is going to be this section highlighted in blue. So this will be known as the S block. Along with the S block over here, though, what we have is going to be helium. So helium is a part of the S block as well. After that, we're going to have the P block, and your P block is going to be this section in green. This is going to be the P block. And then in the middle, that's going to be highlighted in yellow. This is going to be the D block. And then the last block that we have is going to be this block down here at the bottom, which is going to be known as the F block. So these are going to be the different orbitals that we have within the periodic table. So we have S, P, D, and then F. Let's go ahead and take a look at hydrogen. So how we're going to read this is that we're going to read essentially the periodic table like a book. And whenever we're reading a book for the first time, we need to start at the beginning. And so we are going to start at the beginning right here. So this is energy level 1. We enter into the S block, and it takes us 1 electron in order to get to hydrogen. So the electron configuration would be 1s1. If we take a look at helium, we're going to do the exact same idea. Reading a book for the first time, we always start at the beginning, so energy level 1. We enter into the S block, and we have 1, 2. So this is going to be 1s2 as the electron configuration for helium. Getting a little bit deeper, looking at lithium. If we take a look at lithium, reading the periodic table like a book for the first time, we have to start at the beginning. So we're starting at energy level 1. We enter into the S block, and it is able to hold 2 electrons. So this is 1s2. Now, once we reach the end of the periodic table to the far right, we then drop down an energy level. So now we're going to be in energy level 2. We enter into the S block, and it takes us 1 electron to get to lithium. So we end up with 1s2, 2s1. Let's take a look at beryllium. Starting from the beginning, we're at energy level 1. We enter into the S block. It is able to hold 2 electrons. Now we drop down an energy level. So now we're in energy level 2. We enter into the S block, and it is able to hold 2 electrons. So 2s2 would be the electron configuration for beryllium. Now taking a look at nitrogen. Same idea. Energy level 1, we enter into the S block. It's able to hold 2 electrons. At the end of the periodic table, we move to energy level 2. We enter into the S block, and it is able to hold a maximum of 2 electrons. So this is our 2s2. But we want to get to nitrogen, so we are going to continue along with this to the right. So we are still in energy level 2, but this time we are entering into the P block. And then the P block, in order to get to nitrogen, will be 1, 2, and 3. So we get 2p3 as the electron configuration for nitrogen. Let's take a look at magnesium. Starting from energy level 1, we enter into the S block. We're able to hold 2 electrons, so 1s2. Moving to energy level 2, we enter into the S block. It's able to hold 2 electrons, so 2s2. Keep on going all the way across. We are still in energy level 2. We enter into the P block though, and this is able to hold a total of 6 electrons, so 2p6. We're at the end of the periodic table, so we need to go to the next energy level. So now we're going to be in energy level 3. We enter into the S block, and it takes 2 electrons to get to magnesium, so we get 3s2. Let's go ahead and take a look at our iron, our Fe. Same process as before. Energy level 1, S block, able to hold 2 electrons. Moving to energy level 2, S block, 2 electrons. All the way across, energy level 2, we enter into the P block though, and it is able to hold 6 electrons. Moving to energy level 3, we enter into the S block. It's able to hold 2 electrons. We move on over. We're still in the 3rd energy level. We enter into the P block, and it is able to hold 6 electrons. Now we're going to move to energy level 4. Moving to energy level 4, we first enter into the S block, and it is able to hold 2 electrons. Now, moving into the D block is a little bit weird. So the D block is actually a lower energy level than what it's like stated on the periodic table. So whenever we go into the D block, we're going to reduce the row number by 1. So this will actually end up being 3D. So this will be our 3D. And in order to get to our iron, it'll be 1, 2, 3, 4, 5, and 6. So 3D6 will be our electron configuration for our Fe. So just remember that whenever we enter into the D block, we are going to reduce the row number by 1. Let's go ahead and take a look at our AU. So looking at our gold. Starting in energy level 1, S block can hold 2 electrons. Energy level 2, S block can hold 2 electrons. Moving all the way across, energy level 2, enter into the P block, and it is able to hold 6. Keep on going, energy level 3, S block, 2 electrons. Move all the way over, 3rd energy level still, P block, it can hold 6. Drop to energy level 4, S block can hold 2. Entering into the D block, we reduce the row number by 1, so it is our 3D, and it is able to hold a maximum of 10 electrons. So this will be 3D 10. Now, whenever we go back into the P block with this, we go back to the original row number. So the original row number was 4. So our 4P, 1, 2, 3, 4, 5, 6. So 4P6. Moving to energy level 5, so 5S2. Entering into the D block, reduce the row number by 1, so our 4D, and this will be able to hold 10 electrons. Going into the P block, we go back up to the original row number. So this is our 5P6. Moving to energy level 6. So we are 6S2. Now, what we have next is going to be this black line. This black line is telling us that this is moving down to this F block now. So we go from the S block starting in energy level 6. So it'll be our 6S, and then we move down to the F block. Now, the F block, kind of similar with the D block, is it is actually a lower energy level for these electrons. And so for the F block, we are going to reduce the row number by 2. So this and everything will end up being 4F. So this will be our 4F, and the F block is able to hold 14 electrons. So this is 4F14. Now, going into the D block, we're still reducing the original row number by 1. So this is going to be our 5D. And then looking at our number of electrons in order to get to our AU, our gold, this will be 9. So 5D9. And that is going to be how we look at the electron configuration for gold. The reason that we have this configuration is because it does go through all of the different rules of electron configuration. We do have our row numbers. Entering into the D block, we reduce the original row number by 1. Whenever we enter into the F block, we reduce the original row number by 2. So this does hit all of those ideas of electron configuration.